the author of GettingDataScienceDone.com. He's the chief scientist for the ad tech company Playground XYZ, and he's an affiliate researcher with the Transitional AI group at the University of New South Wales. He has 20 years of experience in solving problems in industry and academia, delivering data science solutions for organizations in software development, banking, insurance, media, ad tech, and biomedical research. He holds a PhD in computer science from the University of Queensland, an associate degree in information technology from Southern Cross University, and a Bachelor of Arts in philosophy from the University of Newcastle. He's also written more than 20 peer-reviewed academic articles and presented at academic and industry conferences around the world. So welcome, John.
Awesome. Thanks, Alex. Everyone hear me all right?
Yeah.
Great. So this is a pretty ambitious talk. We're going to cover a lot of material, but the goal of it is less about, say, going into all of the fine details in every technique and more about sort of some of the history and developing the intuitions so that when you sort of see things, these different ideas of dealing with text, they don't seem completely foreign, and you've got enough of that high level intuition that you can sort of dig into them and understand them fairly easily. And we're going to go from sort of like the most rudimentary things all the way up to some of the components in state-of-the-art systems. So that's what I mean by ambitious. Given that so it's about a 40-minute talk, please just sort of jump in with questions as we go through, because it's probably better off because there's a lot of material, worthwhile just asking it and understanding as we go through. We can have so it doesn't matter if it takes an hour or so, really does it? Yeah, we can just have a bit more fun with it. Cool. So outline is as follows. I'll talk about at a high level what it is that makes working with text difficult and challenging. And then I'll start going through the sequences of these different kinds of approaches. So we'll talk about n-grams and TF-IDF, which is kind of the first successful general purpose technique for dealing with them. We'll talk about semantic spaces and word embeddings and how they're created, recurrent neural networks, and then the use of recurrent neural networks for translation tasks will sort of lead to an introduction of the notion of attention, and then that leads naturally to a self-attention, which is critical in transformers, which is critical in sort of ChatGPT and GPT-3, etc., which I said I wasn't going to mention, but now I've gone ahead and mentioned it. Text. What's the problem with text? Well, there's many, many unusual properties to text. The first thing is that it's variable length. So you could be classifying that's the coffee machine shutting down, I think, yeah. You could be classifying a single sentence, a paragraph, or an entire document. It could be written in many, many different languages, or even be, some text data sets combine languages. If it's people chatting who are bilingual and naturally switch between languages, you can have these multilingual data sets. There can be multiple different ways of encoding that text, and it's not guaranteed that when you get a data set that the encoding is going to be consistent. So you might have some records using Unicode, some of them using some other kind of exotic encoding, and you have to deal with that problem potentially. And then there are many, many subtle types of sources of error and confusion. So typos, people can misspell things. Sometimes there's alternative legitimate spellings, like between US and British English, for example. There can be encoding problems, like the wrong encoding was chosen for the specific characters that are available. Transcription problems, if you're dealing with texts come from audio that they've had to transcribe into text. There can be slang and dialects, and then outright deception. So people can do things in text to try and deceive, whomever, like if they're chatting with sort of an online help system, they might be trying to deceive it in some kind of way. So text has many, many sources of potential difficulties, but really this idea of variable length is one that's sort of this sort of core problem that a lot of people, no problem. Oh, they're not up there. Okay, so people are saying online they need to see them. Oh yeah, okay. So I shared, I think I need to stop maybe. Hey, Xavier, I need to make the screen, I need to make the two screens the same, yeah?
To go to displays.
System preferences, displays, and then mirror.
Mirror or arrangement, arrangement. Yeah, I think,
Mirror.
Yeah. I think you just need to share the one with.
What's that?
So you can just open this one here.
Yeah, and come back to here.
Yes, you can just do slideshow mode.
Is that working
Yeah,
now?
it's fine.
Okay, cool. So that was the outline I just talked through. That was the problems with modeling text that I've just talked through. I'm surprised that you all seem to be following it, given you couldn't see my slides. So I just finished talking about all of the various kinds of problems with dealing with text that you've got, from variable length, many sources of confusion, different languages, different encodings, many things that can go wrong. But really, this problem of the fact that text documents can be variable lengths is a source of a lot of problems and a lot of kind of, I guess, inspiration in dealing with text in machine learning. So, because generally machine learning algorithms require a fixed length input vector. That's how most of them are designed. Now, there are exceptions, like if you're using support vector machines, you can design custom kernels that can deal with arbitrary kind of data structures that go into them. But that exception, you know, in a sense, it is an exception, and the most of the tools you'll pull out of any kind of like say scikit-learn or any kind of library of different machine learning algorithms expect a fixed length input vector. So there's a number of different, and in a sense, the way you approach using text in machine learning is largely about how do you solve this problem? How do you encode an arbitrary length sequence as a fixed length vector that the model can deal with? Now, the simplest approach is doing n-gram models, which I'm going to deal with a little bit more next. But of course, you can use regular expressions to do sort of very custom feature engineering. If you know there are certain kinds of patterns that are relevant to your domain, regular expressions are really helpful, but they're not something you can easily reuse over and over again, which is why these n-gram models were kind of like the early, really simple strategies. So the basic idea of an n-gram is very simple. You're deciding some kind of what's the rudimentary component of the text, typically a word, and then you'll have some number of them that you want to encode. So the n is that kind of variable. If it's a unigram, it's a single word encoding, which is what we also call bag of words. It could be a bigram, so 2 word components, and you take your original data set, you scan it to determine what the vocabulary is going to be, i.e. all of the sort of words or components of words that you'll accept, and often you'll filter out the less frequent ones. And then you encode, you basically then encode the data by the presence or absence of those particular unigrams or bigrams, etc. So here's a really trivial example. If we have these 2 sentences, the quick brown fox and how now brown cow is our entire corpus. And I'll try and introduce every term as I use it. So the notion is, so natural language data scientists will refer to their data sets as corpus. It just means like collection of documents. So if we've got these 2 sentences and we want to encode them, we've determined that our vocabulary only consists of these 8 words. And so when we encode the top one, we just have a 1 in the kind of position in the vector where that word appears and a 0 if it doesn't. Yeah, so really simple. This is kind of a unigram encoding of those two sentences. Now, what you put inside that vector can vary. It could be a binary indicator like what I've done there. It could be a count of the number of appearances, or you can use something like term frequency inverse document frequency, which is what we'll talk about next. But the idea is the exact content can vary, and TF-IDF for a long time was this it was like the Swiss Army knife of dealing with text data, really useful for a number of reasons. The first one was that you would encode your word tokens, or they could be n-grams, bigrams, etc. That is for the occurrence of that particular word or phrase in your document, but then you multiplied it by this inverse frequency of how often that particular token appeared in the rest of the documents. Now, and actually those 2 components in this kind of dot product at the bottom here, there were variations in how you could represent them. So the term frequency could just be the simple counts. It could be normalized by the total number of words in each document, so that you're sort of controlling for the fact that documents can be different sizes. You could take logarithms of it to sort of for additional kind of regularization. And then similarly with the inverse document frequency, there were different ways of encoding that. So part of the reason why TF-IDF was so useful for so long is that you had this combination of both representing the presence of keywords in your document. You were also taking into consideration how rare or frequent those terms were across the entire data set. And because there were different ways you could encode it, there were things that you could tune in a kind of hyperparameter tuning session. So it was very, very flexible. However, so which begs the question, if it was so useful for so long, why did we start moving beyond it? And the reason is that it only can capture certain kinds of properties of text. So essentially, at essence, it's saying, are there certain words or phrases that are informative for the task that we're trying to do? And is the pattern of the frequency or scarcity of those words something that's useful for the task which we're trying to build a model for? So in general, N-gram models are very poor at representing meaning in text, unless the people are using a very, very restricted vocabulary, because as soon as you have lots of synonyms for a certain, or sort of expressions or unusual ways of expressing the same thing, the N-gram model struggles to represent it. And it's particularly bad at representing things that will depend on fairly long-range linguistic structures in language. So for example, embedded clauses is a great example. Let's say I'm trying to build a model that predicts how readable a block of text is, and one of the features might be embedded clause. So an embedded clause is, I might be talking about a sentence, could be simple, could be complex, but I want to understand the content of it. That section in the middle, which you could imagine was kind of bounded by commas, is an embedded clause, and you can have many, many embedded clauses, and in certain languages like German, it's almost like a high art form, how many embedded clauses you can have, and N-gram models can't represent that. So in some sense, there's patterns to language which depend on the order in which they appear and the kind of syntactic structure. So that's kind of a justification for why we really need systems that move beyond N-grams. So semantic spaces is one of the next kind of key things that became really, really useful in language processing. And so the idea here is, can we represent words and phrases as a numeric vector that represents the meaning? Yeah, so let's take these two sentences, for example. The dog jumped over the fence and the hound leapt across the barrier. In essence, they mean the same thing, and you want a system that can generate a vector of numbers where these are basically identical, and the N-gram model won't give you that. So sort of super quick primer on neural networks, because most of the rest of the talk depends on the ideas here. Actually, quick display of hands. Who here has worked with neural networks? Yeah, roughly half of people. Okay, cool. So the basic idea of neural networks is that you'll take some raw data set and it will be encoded in that initial layer of nodes, and it will be processed through several layers of nodes and processing before you get to your final layer, which is where the signal, you're expecting it to produce your output and prediction, and you're feeding information back from those final layers. And one of the key insights, this is the thing that you kind of need for the rest of the talk, is that those intermediate layers, the hidden layers, can learn representations of that data that are useful in many, many different ways. And so they will get used to generate semantic spaces. So that's the kind of key thing to keep in mind, reuse of the contents of hidden layers. So word embeddings, popularized heavily by Word2Vec, but there are many other ways of approaching this. They learn to create these semantic embeddings of words through a relatively simple task, which is basically, can you predict the relationship between one word and the context words, which is all the words that appear around it. Now, there are two general approaches to doing this, continuous bag of words and skipgram, and I think various iterations of Word2Vec have used both of those. And in both instances, the hidden layer ends up being used as this semantic representation. So I think the final version of Word2Vec used the skipgram encoding, and this is one of these initial versions of what we now tend to refer to as self-supervised learning, where you can just take large amounts of text and learn a model from it without any other explicit labels. So what they do is they take their corpus of text and they move a sliding window across it, where, say in blue here, we have the target word, and the size of the window around it encapsulates all the context words. So you can extract this training data that consists of target word, context word pairs, and the number of them will depend on how large your training window is. And so what you're going to try and predict is the distribution over context words given a particular target word. That's the kind of essence of the skip-ram model. And so on this, on the right-hand side, you see what that looks like. You'll have, say, a one-hot encoding representation of the target word through the hidden layers, and there'll be multiple samples of all the different context words that appear around that, each with their own one-hot encodings. And so what you end up learning is this probability distribution over potential context words. And at the process, after you've trained that model, you can then feed the target word in and extract the activations of the hidden layer, and that is your semantic embedding of that particular word. Is that clear to everyone, or am I just telling everyone things they already know? Yeah. So the surprising utility of this is one of the ways that we know that it gave us a sense of the semantic representation of the words is that you could perform simple algebra on it. So has everyone heard that example of like that you take the semantic representation of king, you subtracted the semantic representation of man, added in the representation of woman, and you got queen. So the fact that we could do this algebra on these semantic spaces gives us some confidence that it is representing something like the human idea of meaning. So these turn out to be really useful as a new way of encoding features about the content of sentences for machine learning models. However, they did have limitations. You note that still, even if you take all of the words from an arbitrary length sequence and convert them into semantic representations, you're still back to that original problem we spoke about at the start, which is it's a variable length encoding. So if you're going to feed that semantic representation into a machine learning algorithm that expects a fixed length encoding, typically what people did was take that semantic algebra idea and they just add all the vectors together. So you take all of the word embeddings of all the words in your input corpus for each data row, add them together, and then you've got something that crudely approximates the meaning of that particular sentence that you can use into your algorithm. Works pretty well, but of course it's fairly easy to contrive examples that it doesn't work well. So for example, these two sentences, his writing is not good, and it is good he is not writing. Yeah, if you got the semantic representation of those words and added them together, you would end up with something that's quite similar, but actually the meaning is very different. So, and of course the problem is the meaning of a sentence or a block of text is not just adding up all of the meaning of the individual words. The structure of the sentence itself matters. Yeah. So that's kind of why recurrent neural networks remained useful even after we had these semantic spaces. Recurrent neural networks that had been around for quite a while. And I guess as an aside, I'd been using them in bioinformatics work. So in bioinformatics, we were dealing with protein and genome sequences, which were also arbitrary length sequence structures. But of course, unlike human language, which we know a lot about, so you can use sort of domain knowledge for feature engineering, you don't really know at the start of it what all the embedded structures are inside protein sequences. So we spend a lot of time training recurrent networks to sort of learn the properties of proteins from these sequences. But the basic idea of the recurrent network is that it can process any arbitrary length sequence piece by piece, and it will build up an internal memory structure of what the contents of that sequence is. So here's the intuition. Regardless of how long this input sequence is, you start by first, your recurrent network will have a fixed input window, and it takes in that initial input window, passes it to its hidden layers. You may not have a classifier to begin with, like this part may not be active, but the idea is as you push through the sequence, processing subsequent sections of the sequence, they get passed to the internal hidden nodes, but you also pass the activation of those hidden nodes from the previous time step in this recurrent way. So these are very specific weights that tell you how you retain a memory of what's happened historically, and you do that as you move all the way through the sequence. So when you get to the very end of the sequence, this hidden state then now contains a representation of that sequence, of the entire sequence over time. And so early papers on recurrent networks show that they could do really, really interesting things. Like they could act like a sort of a stacked memory layer. So they could like push things onto a stack and pop them off again, and they'd actually carve up if you think of the hidden nodes as in this example, 3 nodes as a 3-dimensional space, they could create fractal structures inside their hidden space and then unwind them again if you were teaching them to sort of do counting tasks. So they were able to learn to use their internal memory structure to do really, really interesting things. And they turn out to be really useful for a lot of language tasks as well. So, but they, in particular variations of them, so the one you've probably heard on is the LSTM, because it seems to have dominated all of the use of recurrent networks in these days, which was a variation deliberately designed to help you learn longer range structures inside data, but they still have lingering issues. So they tend to emphasize the very last part of the sequence they've processed, in part because the vanishing gradient problem never went away. So the idea of the vanishing gradient is, it's the same as it is in, say, really, really deep networks. The further you go back in time, the harder it is for the signal to reach, to affect the tuning of those parts of the network. And that the second major reason is that because recurrent networks are inherently sequential, you have to process the sequence bit by bit, so you can't parallelize them. So that's one of the main reasons they've gone out of vogue these days, is because we're so focused on neural network structures that we can process rapidly with GPU units. So that's one of the other main limitations. However, they still persisted for quite a while, particularly in translation, because they were really, really useful at this really difficult task of sequence to sequence. So far, everything I've spoken about is largely about, you've got text, which is a sequence, but your task tends to be something more traditional machine learning, like, say, classifying whether the text is readable or not, or whether it belongs to a certain topic. But sequence to sequence problems are this really unique situation where you've got arbitrary length input and arbitrary length output. So human translation between languages is in this kind of domain where you don't have a fixed length input and you don't have a fixed length output. So really, really hard problem. So the structure that persisted for a long time in translation was this notion of a sequence to sequence model, where you have some kind of encoder that encodes the original language, and then a decoder that decodes it into the language, your target language. So this is what that structure looks like. Basically, you pass a recurrent network over your input sequence. So in this case, the dog is lost. I've introduced this start token here somewhat sneakily. So from now on, quite often, for a lot of these architectures and algorithm designs to work, you need to create a special token which represents the start of the sequence, and there'll be a special token that represents the end of the sequence as well. I've just kind of snuck that in there. So you process that whole sequence to the end. At the end of that process, your hidden nodes now contain a representation of the meaning of that entire sentence, and you pass that semantic vector to the decoder unit. And what it's going to do is it passes that semantic representation through a new network, plus the encoding of your initial, your start token, because that's where you have to start with what the output of the decoder is going to be, and that will produce your first token of the translation. So I'm translating to German here, der. And then what I do is you then pass in the encoding of that first token that you've put into the decoder's output back through this network, plus maintaining your semantic vector, and it's going to produce the next word. So there's this process where this network is learning, okay, here's my representation of the sentence that I need to, the meaning of the sentence I need to produce, and then I'm going to sequentially produce all of the tokens of that in the target language. And the beauty of this structure is everything here can be back propagated. So you can back propagate from, from whatever the content of this, the semantic and the previous token, to what the target token should be. You can back propagate that all the way through to what this semantic representation should be, then back through this sequence. But you don't need to. You can also sort of, like if you've already got a good encoder that works with a translation model, you can cut it off here and you can just retrain this process. So you can say, okay, I've already got it translated to German. Now I'm going to build one for French. So I'm going to freeze this part of the network and I'm just going to train this part that does the coding. So this decoupling of encoding, decoding, and this ability to use a semantic representation to generate an arbitrary length sequence was really, really powerful. And it should sound familiar because a lot of these ideas get reused in the transformer architecture, even though it isn't a recurrent network. Does that make sense to everyone? Everything I've said, more or less? And I said, sorry, before the people that came after, I said, interrupt me with questions if anything's not clear, because I think we've got plenty of time to have a good discussion if there's anything you want to dig into. Yeah, cool. So that is your encoder decoder architecture. Now this structure still has some problems. So one of the problems is that that final node activation layer as a semantic vector still has problems because it's still relying on the fact that you've got to get all the way through this sequence to have this semantic representation, and all of the problems of recurrent neural networks with sort of the vanishing gradient and the overemphasis on the last parts of the sequence still exist. So it's an imperfect semantic representation of that target sentence. So this is where the idea of attention came back into machine learning. It existed before. There'd be people who'd been experimenting with it, but this is the particular application where it really came back into vogue. So the idea is we want some mechanism that allows the architecture to learn, allows us to use a richer representation of that entire target sequence. And so that it knows what it needs to attend to about that target language at each part of the production of the output. So here's the intuition. Again, I've just taken away the recurrent connections there, but again, we're going to use a current neural network to encode the target language. But rather than just use the final activation state of the network, we're going to keep all of the hidden node activations all the way through this process. So we've got this arbitrary length stack of hidden node activations that depends only on the length of the input sequence. Yeah, so this thing could be any length at all, totally open-ended. And now what we're going to do is we're going to start our decoder with a start sequence. But we're going to feed the start token encoding through some attention weights to create this thing called an attention representation. And then we're going to take the dot product, of that attention representation with every single one of these hidden node states, and we'll end up with a weighting for those hidden node states. So what we're basically saying is, given that we're starting at the start token, give me a representation. Remember, this part's learnable as well. Give me a vector which I can apply to all of my hidden node states from across that original target sequence, and it will provide a weighting that I can use for which of these things I should pay more attention to. So it's in effect, it's trying to learn which of these, because remember, some languages, the subject order, the subject, object, predicate, the ordering can vary. So it has to learn how to find the most important semantic representation in this stack in order to attend to. Once I've got those weightings, I then take, basically, I apply these weights to these hidden node activations to get this attention sort of attenuated hidden node representation. So the dimensionality of this is the same as my hidden node, original hidden nodes, because it's just a weighted sum of each of these columns. And then it's this thing that I feed through whatever the network structure is here. I've kind of left that out, but you've got some network here that you learn that produces the next token in your output sequence. And then we repeat the process. I then feed whatever token I've produced through my weights that provide me an attention vector. I take the dot product of that against all of my hidden node representations again. I get a new set of weights. I do a new weighting of all of these hidden node activations, and that is used to learn my next output of the of the decoder. Does that make sense to everyone? I'm hoping the colored boxes make a little bit. Don't worry about the maths. I'm just, what I'm hoping is the intuition is, because all of this is learnable, seems like magic, but again, you're just back propagating the whole lot. You're saying that there should be some information in the word that I've just output that I can use to work out what I need to attend to in this semantic representation of the input sequence so that I can produce the next representation that will allow me to produce the next word. Yeah. So that's the kind of the idea of attention, and it's amazing, really. And so this was like in about 2014, got incorporated into Google Translate, and there was a really massive change in how well Google was able to do machine translation at that point in time, basically because of this technology. And then, crazily enough, it didn't stop there. So that led into the inspiration for the self-attention mechanism in transformer models. Now, because there's certain things. First of all, this attention mechanism only really worked in that particular architecture where you're doing sequence-to-sequence modeling, and it still required these recurrent networks to do all the processing. And so the idea in the attention is all you need paper. There's many, many ideas in the attention is all you need paper, but part of the idea is to do really efficient sequence-to-sequence modeling without these recurrent units, and it had all kinds of other side effects, the fact that you could use it for a whole bunch of other tasks as well. But the key idea is, if you're not building up this recurrent semantic representation that can be then collapsed into a fixed length window with attention, how are you going to do that? Because you need something fixed length in order to parallelize it, because that's one of the key things they wanted to do with transformers. So the part we're going to focus on, I'm not going to talk about most of the transformer architecture. I'm just going to talk about these multi-headed attention components, because it's really, first of all, for me at least, it was the thing that was completely unintuitive. It took me a long time to understand what was happening in there. And then I think the rest of it's it's complicated, but it's understandable once you understand how multi-headed attention was. Now, first of all, multi-headed attention means that you're just going to do the thing that I'm going to describe next many, many times. So the core of multi-headed attention is a self-attention mechanism. And the idea of self-attention is that we will start with some kind of representation of a sequence of words. So I took this example from the Rasa whiteboard series. They've got a really good YouTube series explaining a lot of NLP stuff. And it's a good example because the sentence, the bank of the river, if you used a standard kind of semantic representation, you probably would use a bank that indicates a financial institution. But the idea of self-attention is, if you re-weight the semantic representation of all of these words, taking into consideration all of the other words in the sentence, then the bank one will probably shift, because the word river is really critical, and it'll know that it's this other kind of bank, not the financial institution. So that's the target state. Basically, take a sequence of word representations, but adjust them in this kind of using this self-attention module, so that they take into consideration everything else in the sentence. So the core of self-attention is we have to take the representations of each words, and we generate these three things called the query, the key, and the value. And they're used inside the self-attention mechanism. And the way the way it happens is, let's say we're going to try and create the new encoding of the word bank. I will take my query representation. So remember, this query thing here, set of learnable weights, it's just something that transforms a representation of bank into a new representation for querying. I'm then going to take the key representation for all of the words in my entire sentence. Again, this is a learnable set of weights. That's just something that transforms one representation into another. And then I take the dot product of them. So I go through all of these things, and I'm basically saying, here's my query, how similar is it to the key of all of my other words? And I'll get a new kind of weight, just like I did in the previous example. And then what I do is I'm going to have my value representation of the word, and I'm going to weight that value representation by the specific weighting that's come from the query key dot product that I've done here. Yeah, it's probably worth mentioning, I think in the standard transformer implementations, this value, these weights are actually just passed straight through. You just keep the original representation of the word. But in principle, there's nothing stopping you sort of learning new representations if you wanted to. So basically what ends up happening is, again, this new representation of the word bank is now a weighted sum of each of these representations of all the words in the target sequence weighted by this result of the dot product between query and key. Now you might imagine in most instances you want the one for the actual word bank would be pretty strong, and most of the weighting would be on that. You don't want the representation to change too much, but it should be subtly influenced by all of the other words in the sentence. So that what we end up with is this new representation of bank that has taken into consideration every other word in the sentence. And part of the power of transformers is we don't just do this once. The multi-headed attention, we do it many, many times. So it actually learns many, many different ways of taking into consideration everything that's happening in a sentence. So you end up with this really sort of complex representation of the sentence at the end of the process. And so all of these words are being transformed in parallel multiple times. They're then recombined into a vector representation. Typically what happens is you use the encoding of the end token for a lot of heads that are doing things like sentence classification. I'll use the encoding of just the end token at the end because a little bit cleaner, and then that way when you back propagate, it's just learning in some sense a semantic representation of the whole sentence. Yeah, fine. Yeah.
So why it's called self-attention?
Yeah. So because if you come back, so the idea is the self here is the sentence. So that every word in the sentence, it's paying attention to itself. Each word is paying attention to itself and every other word in its own sentence. Whereas the attention in the translation module, it's like it's saying, okay, I'm translating from this language to this language. It's the target language paying attention to the content of the source language. So it's not paying attention to itself, it's paying attention to where it's coming from. Whereas here, it's the block of language is paying attention to itself.
So
At least that's I actually don't know. That's my interpretation of it.
key query are both from the same sentence.
Yeah. And so the other side effect here is like and I know several people here have been using them as well. You can use these. So the BERT model only does this encoding part, where basically learn a contextually sensitive representation of language, and you can put sort of classifiers on top of that for different kind of language tasks. But there's a whole decoding module that also does the same, the whole process again, but then it takes the semantic representation from a self-attention encoder and then generates sequences from it. So it's turned out to be this amazingly powerful general purpose technique. I think it's fair to say, I was surprised at how well it works. There are so many pre-trained transformer models. You can grab them and knock off the head, train them on a new task, and get some. Often it can be sort of better than something you've thrown all of your other tricks at. So it's surprising how rich. Sorry, I should say the idea of these pre-trained models is you apply this technique to large and vast amounts of text. So all of these weights for how to generate the query keys values and pass them through are sensitive to large amounts of text, and the way they do it through a masked training process, where you're basically saying, given a block of text, just take one word out and then learn what the identity of that word should be. So similar in sense to, if you remember back to word2vec, where it's saying, given a context, predict a target word. So the same idea has been recycled, the idea of self-supervised learning, where you can learn the structure of language just from the text itself. But now we've got these pre-trained models that you can use for many, many different tasks and get pretty close to state-of-the-art performance. So the summary of everything I've spoken about, we started with the process of the core of doing machine learning with text is how you generate some kind of fixed length feature representation. We spoke about n-grams and TF-IDF. We then spoke about processing sequences into semantic spaces and what that gave us that we didn't have with the n-gram models. We talked about why recurrent models were used for so long, and that kind of, the sequence models gave rise to the idea of attention as a way to provide more contextual information to these semantic vectors, which ultimately led to self-attention in transformers, which has turned it entirely sort of revolutionized the field. Some credit where credit is due. Aside from the papers I've directly referenced, Jay Almar's visual transformer posts are excellent. This guy has an amazing ability to explain complicated ideas. I highly recommend everything he does. The Rasa Whiteboard series, as I mentioned before, and the Hugging Face transformer book is really, really good. So Hugging Face, if you haven't used it, really nicely designed, clean API with heaps and heaps of pre-trained transformer models you can use for various tasks. It's a great resource, and the book they've written about it also has a nice couple of chapters just giving a high-level overview of how transformers work, as well as an explanation of all the things you can do with their APIs. Really, really useful. You can connect with me here. My GitHub bio, I've got like some of my open source projects and things I'm working on, and I've got a book out, as I think Alex mentioned at the start. It's not about any of this. It's about kind of the process of delivering data science projects, sort of like problem framing, talking to stakeholders, deciding on metrics, that kind of stuff. Thank you. Any questions, actually? Oh, sorry. I'll let you clap, Desmond. Thanks.
Any other applications that you could actually give example that these text bioinformatics, for example,
Yep. Yep.
whether only by
Yeah. I know that there has been experimentation with attention mechanisms in time series forecasting. I don't know anything about it. I just know that it's been done. I don't know how well it works. But I was going to say, sorry, I've forgotten your name. What's Jesse? Jason, yeah. So Jason was talking before. He's been using transformer models for text classification, yeah, or sort of topic modeling. Both. Okay, yeah, both. Do you want to sort of explain the it's an interesting application where you don't even, your topic modeling on language that you yourself don't speak, is my understanding.
For topic modeling, we first use to convert sentence into vector.
Yeah.
Then we can apply clustering algorithm to group those vectors into different classes.
Yeah.
Each class will be a topic.
Yeah. Yeah.
It's a usual answer actually.
It was Bahasa, wasn't it?
Yeah.
Yeah.
Yeah. That's the model for multi-language.
Yeah. Yeah.
I think Ben has a question on what are some fun things you can do with BERT?
Fun things you can do with BERT.
Yeah.
So, I mean, I can talk, a side project I'm working on, I was explaining to a few of the team earlier before we kicked off. Australian College of Surgeons is a sort of medical research organisation in Australia. They've been doing, so in biomedical research, literature reviews are really, really heavily sort of structured. You know, they actually, because you want to basically know that before you engage in some particular bit of medical research that you've read pretty much every important paper on that topic. So they actually have organizations who perform contracts to do that literature review for you. They actually, they have a team of people whose sole job is to read medical literature. Well, they've got several skills. One is how to conduct literature database queries to find all of the relevant papers, how to scan them and know which ones are relevant to that topic. But the problem they have, so Australian College of Surgeons has a team that does this by a contract in Australia. but they've got this problem that the volume of medical literature is growing, not quite exponentially, but sort of like very, very rapidly. And so it's a harder and harder task to scan all of that literature. So we've been working on using transformer models to basically, someone comes and has a description of the medical problem they have, which will be this kind of treatment, people exhibiting these kind of symptoms, and these are the kind of like side effects or whatever we want to have been testing for. So that's the description of the studies they're looking for. And then we've got a massive data set of abstracts of biomedical papers. And the target is basically saying, is this abstract likely to be, is it in the set of things that the literature reviewers have to look more closely at? So we're only looking at the first stage. It's like you take a list of 10,000 papers and you want to whittle it down to the 2,000 that the reviewers actually have to read in order to identify the 100 most critical. So we're just doing simple things where we take, there's versions of BERT available on Hugging Face that have been trained purely on biomedical research papers, so it's sensitive to the way medical language is used, and then we feed it in a concatenation of the research question, the abstract from the paper, and then we just chop off the head and we train a new head to predict basically should it be included or not. And it works amazingly well. So I've tested a whole bunch of just like my standard tool of the, tools of the trade, machine learning techniques using TF-IDF and a whole bunch of other stuff. And I've got a bunch of models. I've done one epoch of training with this BioBERT one, and I, like half of my test cases, it's already better than all of my other ones. It's kind of unfathomable, really, how well it works. Xavier, you were going to say something before, yeah?
Yeah, just a question. Do you expect more innovation in the techniques, or
Yeah.
do you see it as a setback potential?
Yeah. I mean, I think there has to be. I think so. I mean, one of the limitations that people don't talk about that much is that these, like, one thing that we still haven't dealt with is transformers don't deal with arbitrary length input sequences. Like the input window is actually fixed. They train them with quite large input windows, and there are ways of tricks of the trade people use for getting past that, but they're not. It isn't an arbitrary length input sequence, and the other thing, I mean, I think the thing that we'll see is once the new wave of hype dies down around ChatGPT, etc., we'll realize that it's not. We will need new kind of architectures to deal with certain kinds of problems. So here's something that's still like I've just been trying to put this down into words in the last few days, so I don't know if I've got it exactly right. If you think about the way ChatGPT, I'm talking about it again. I said, what am I going to talk about? The way, so ChatGPT, it's basically, it's a model that says, given this long block of text, what's the next most likely bit of text to appear? And because it's been trained on so much text, and you can prime it with what the prompt is, and the series of questions and answers it's given, it's able to give really, really amazing next kind of outputs. But its entire notion of the world is embedded in two things. One is the statistical model of the next most likely word, and the other one is the context, which is the prompt and everything you've just given it. And yet we're expecting it to be able to do reasoning problems. So people throw reasoning problems to ChatGPT. But the issue there is that you can pollute, like the history of what you've said to it pollutes everything that it's thinking about and how it's going to generate the next word. Whereas we know we don't do that. We have internally, when I'm having a dialogue with someone, I'll have a model of how I think the world works or how I think this topic works. They will say things to me. I'll have a model of what the semantics of what they've said to me is. And I don't automatically just agree with them and then chug on like that's my new version of the world. So with ChatGPT, if it gives you an answer and you say, no, you're wrong, it just goes, oh, I'm wrong. Oh, and then it comes out with the most plausible next thing it should say after that. So it's got no notion of a model of the world that has to be coherent. that is robust to sort of attacks. And so I think we need one of the next rounds of innovation in this space will be some notion of where you can have the dialogue system, like what ChatGPT Transformer can do, that has to cohere with a more robust model of the world that is it's more resilient to change. And I mean, obviously that's what Microsoft is going to have to do if it's ever going to be useful for search. But who knows if that innovation is going to come out of Microsoft or not. I don't know. Does that?
Is the reason, like, I think there's something that's hallucination right now where
Yeah.
ChatGPT tells you like extremely wrong things. So this something that you probably be better in the next few versions. So
I don't know. I mean, the hallucination is because the way I try and think about it is you have to think about what has ChatGPT been trained to do. What's the target function? It's basically plausibility. It has to produce output sequences that seem plausible. They don't have to be truthful. They just have to look like they could be true. That's its target function.
Sorry for deviating from ChatGPT. Coming back to the Transformers model.
Yeah.
Since you were discussing about use case I was talking.
Yeah.
In fact, even I was working on when I was working with the insurance firm, I was working on a similar medical use case.
Yep.
But I was working with BioWord as well.
Yep.
How many lines of data, let's say, how much data do you think is like good enough to fine-tune model as big as BioWord?
Yeah, I don't know. Like I've got 300,000 records, and it seems to be working really well on this one particular use case. But I've been like these guys, you know, it took me ages to get the data out of them. I'd been talking to them for several years, and over the last year, it's just been okay. What's some research questions you've done historically? Do you have those CSVs and Excel files lying around? Can we get them out? Can we re-extract the abstracts from all those papers? Because they've done that hard work of labeling all of the abstracts that were relevant for that particular research question. So, long-winded question. I haven't done enough experimentation with BERT to really know.
In my use case, I had just about 3-4K data points as well.
Yeah.
But in my case, actually a deep learning model was performed better than BioWord.
Yeah, right.
So mine was a classification problem with 250, more than 250 tables.
Mm-hmm.
That is by the reason behind this accuracy. But just out of curiosity, did you like play around ancient heads as well by
No. Yeah, I've just chopped off the head and replaced the head. I haven't modified the actual model itself. There are things that I'd like to do that are on my list, but no, I haven't yet.
Have you used any of those to control?
I don't know. Yeah, no. Actually, so I did. I was talking to the Australian. There's a school of management studies in Australia that I came in to give a guest lecture just about data science and analytics for those people doing MBAs. And the lecturer there, I've been speaking to him about doing a book because this book's more about. So one of the difficulties a lot of data scientists face, they're used to sort of thinking just about technical problems and very deep in the details, dealing with other technical people. You get into organization, all of a sudden you're dealing with business people and executives and operations people who have different understandings of the work you do. And so you've got a communication challenge in many, many regards. Like you've got to, first of all, extract enough information from them in order to know what the solution is going to be. And then you've got to work with different people to embed it. So that's what that book was about. But he's been talking to me about doing a book about them from the management's perspective, like trying to train managers to be better leaders for data scientists. And I did have a crack at seeing how ChatGPT would go with writing the first chapter. It was terrible. But I also, through that process, I also learned that I'm not very, like, the art of writing the prompt is critical. So like as I was doing that, I was learning more and more about the prompt component. So I don't know if it could better. I've tried to get it to write me a sci-fi novel. It was also terrible. It seems like, I don't know, it seems to be good at writing sonnets and rap lyrics, but as far as I can tell, it's other than that, I'm not crazy about its creative output. I don't know. Has anyone got a great story of like a creative thing they've got ChatGPT to do that's astounding?
Currently, I write a documentation.
Yeah. Yeah.
It's good for web chat.
Yeah, awesome.
And when you can notice when you wrote something that is not clear because
Yeah.
you ask to rewrite what you wrote, but you get back doesn't make sense. So but often it's close to what that's.
Yeah. Yeah.
So,
Are you
yeah,
feeding,
so-
are you, oh, sorry, are you giving it like code snippets as well for the documentation, like API sort of documentation, or no?
No, it's not, yeah. It's writing the glossary and chats. So, okay.
Yeah, right. Interesting.
Try to have a classification. Glossary of the definitions. Yes, it's what useful when you want to write things fast. You can get that.
Yeah.
At the end, yes, it's not the final version. Good, it's especially for non-native English speaker.
Yeah. Yeah, cool.
The generalization of the responses, which have been so you see that the responses come back more masculine.
So yeah, in French you have a gender.
Yeah, I've heard it's good. So I have colleagues who use it for like code explanation. They'll put in a block of code and ask it to explain it to them. They say it's really, really good for that. I've used it for writing some functions, but I found that I have to be very explicit about what I want the function to do. And then often I then have to prompt it and say like, no, change this style because that what you've done there is inefficient. But I was also saying to the team before, there's a really amusing Twitter thread. This developer got really excited about the coding abilities of ChatGPT and decided he was going to write an iOS application because I think he'd seen there was a couple of posts where someone it had written some rudimentary Swift for a couple of iOS functions. So we started to write this whole application, and then it was going great. Like he had some initial prototype running, and then like by the end of the second day, I can't remember how far into it anyway. Then all of a sudden he started encountering dependency problems between getting different things to work with each other, and then the whole thing would compile. And so he like ended up abandoning the project. So I think because the problem is going to be the more concise the task is, the more likely ChatGPT has been exposed to data sets that can help it sort of generate that one thing. But the more integrated the solution you're trying to build, where it's having to sort of, you have to like imagine trying to cobble together a solution from 100 different Stack Overflow pages and just expecting the whole thing to work.
It doesn't work. I know some people try to use the hackathon questions for ChatGPT.
Yeah, okay.
The hackathon has the simple, medium, and advanced.
Yeah.
It does reasonably well for the simple ones, but for the advanced ones, it's like terrible.
Wow, really? Even with that, and because that's like specific algorithms, I would have expected it to do well. Yeah.
But it doesn't work like that.
Yeah. Yeah, it's weird. And there's another example. There's a really good Twitter thread, because the other thing that I've wondered about it too is we don't know. People are getting very, very excited about it, posting really examples of it doing amazing stuff. But because we don't know what the training data set was, we don't know if it was just testing on the training data set. Like so there's an academic in the US who posted an example where you could sort of, he was sort of looking for ways to test what's in the training data set and what's not in the training data set, and ways to sort of expose that in the way you prompted it. I can't think of the exact name, but it was about asking it to explain certain kind of academic papers, one of which he knew had to be in the training data set and one of which, you know, probably wasn't in the training data set. And you could find this divide really, really quickly. So I wonder whether a lot of it is that, but it's super surprising that the HackerRank stuff isn't in the training data set. Yeah, yeah, maybe, yeah.
I think the accuracy for the beginning of the question and HackerRank is 50%. But what universal question is just 10%.
Yes, yes.
Yeah, right. Wow. Yeah. Hmm. I mean, it's going to be interesting to see. I'd love to see like a code off between Copilot and ChatGPT. Like, will they end up having that? Like, you know, like we've had these kind of robot wars for a long time. You know, where people build robots to go and fight. I want to see like the sort of transformer HackerRank. Just let various large language models sort of compete in a hacking competition. It'd be great. Does anyone know much about the details? So apparently, with the GPT-4 release, there's information about how they hired a consulting company to test whether it could escape. Does anyone know about this? No? So prior to the release, I think it's in the GPT-4 white paper, but I'm not 100% sure. It could come from somewhere else. They hired a consulting company that ran some tests to see if, in principle, GPT-4 could Skynet itself, basically. So they had like a read-print loop state, so where GPT-4 could just continually interact with itself, and they gave it the ability to spin up copies of itself to sort of go of sort of subtasks, and an ability to spin up compute tasks, I guess, in the Azure cloud. And they're trying to test, you know, if it was able to escape the Azure cloud. Which is, I mean, it seems weird that they'd want to, like, maybe I'm naive. I think it seems unlikely that it'd be able to do that. But it is interesting. We've reached a point in history where is this going to become a thing for future releases of large language models, that there's companies that test whether they can Skynet themselves. What's that? Yeah. Mm. Think we're done? No questions online?
No, Ben is excited about the robots.
Awesome. Awesome. Well, thank you very much, everyone. Thanks. Oh. Has that got a power button on it? Oh, you've got that. Cool. Awesome.